Good day. For those of you who do not know me, my name is Douglas Harder, and in this topic, we are going to look at the properties of the adjoint. So in this topic, we will deduce a number of properties of the adjoint, and we will observe that these properties are very similar to the properties of the complex conjugate. Recall that given two linear maps A and B mapping a vector space U onto a vector space V, then if the inner product of A times any vector U in the first vector space and any vector V in the second vector space equals B times that first vector and the second vector for all possible vectors in the two vector spaces, then the two linear maps must be equal. Theorem. The adjoint of a linear map is the linear map itself. To prove this, let's just use the definition of the adjoint. Given the matrix A, I can move that matrix to the other side of the inner product by using its adjoint. Now, from the properties of the inner product, we have that the inner product is conjugate symmetric for complex vectors and symmetric for real vectors. But in either case, this is true. Consequently, we can now look at the inner product. Now, here we have the inner product of the adjoint of A. Okay, well, we can actually move that to the other side by taking the adjoint of that adjoint. Now, using the properties of the inner product again, we get that the adjoint of A multiplied by U, the inner product of that and V, that must be equal to the inner product of A times U and V for all vectors U and V. Therefore, those two linear maps must be equal. Theorem. The adjoint of a linear combination of linear maps is equal to the conjugate linear combination of the adjoints of those linear maps. Okay, let's try to prove this. Well, by definition, the adjoint of that linear combination of linear maps is equal to, we can bring that over to the other side of the inner product, just that linear combination of linear maps applied to U. But the inner product is conjugate linear in the first argument, and therefore we can take out the conjugates of the scalars. Now we can bring the adjoint back to the other side of the inner product. Now the inner product is linear in the second argument, so we can just bring the conjugates of the scalars into the second argument. And from the properties of the inner product, that equals this, and consequently we have proved our theorem. For real vector spaces, the adjoint is linear. Proof. Well, for real numbers, the inner product is symmetric, and thus we may modify the previous proof to show that the adjoint of a linear combination of linear maps is equal to that same linear combination of the adjoints of those linear maps. Next, let us consider composition of linear maps. So if A maps a vector space U onto V and B maps a vector space V onto W, then the adjoint of B times A, or B composed with A, is equal to the adjoint of A composed with the adjoint of B. If these are matrices, then the adjoint of a product of matrices is equal to the product of the adjoints in reverse order. Proof. Well, by definition, if I am considering the composition of B and A, then the adjoint is that operator that can appear on the right-hand side of the inner product. But looking at B times A applied to the left-hand side of the inner product, we know that that is equal to B applied to A applied to U. Now, A times U is a vector in V. B maps V onto W, and therefore there must be an adjoint of B. So let's bring that to the other side. So now A times U is in V. B star times W is also in V. So we are taking the inner product of two vectors in V. Consequently, I can now bring over the linear operator A to the right-hand side. But by the definition of composition, this is the composition of the adjoint of A and the adjoint of B. Therefore, the adjoint of B composed with A is equal to the composition of the adjoint of A and the adjoint of B. Note that this makes sense. After all, if A maps U onto V and B maps V onto W, then B composed with A maps U onto W. However, recall that if A maps U onto V, then the adjoint maps V onto U. Same for B star. B star, or the adjoint of B, must map W onto V. Therefore, there is a linear map A star B star that maps W onto U. However, from the first, we also see that the adjoint of BA must also map W onto U. So whereas the previous proof demonstrated that these were equal, here we're just observing that at least the vector spaces which are being mapped to each other are indeed consistent with what the theorem claims. Now here, 0 is the zero map mapping all vectors in U to the zero vector in V, and 0 prime is the map that maps all vectors in V to the zero map in U. If that's the case, then the adjoint of the zero map is equal to the zero map prime. Proof. Well, by definition, the adjoint of the zero map is the map that satisfies this condition. However, the zero map applied to U is equal to the zero vector in V, and the inner product of the zero vector in V with any vector in V is equal to 0. However, the zero map 0 prime that maps V onto U also maps the vector V onto the zero vector in U, and the inner product with the vector U and the zero vector is also equal to 0. Consequently, the first two inner products are equal for all vectors U and V, and therefore the two linear operators are also equal. Thus, the adjoint of 0 is equal to 0 prime. Theorem. If I is the identity operator mapping a vector space onto itself, then the adjoint of I is itself. Proof. Well, by definition, the adjoint of I is that linear operator I star such that the inner product on the left-hand side equals the inner product on the right-hand side. However, I times U1, or I applied to U1, is simply U1. Not only that, U2 is equal to the identity map applied to it. Consequently, we note that if the first equals the last for all vectors U1 and U2 in the vector space U, we must conclude that the adjoint of the identity operator is itself. If A is a linear operator and A is simultaneously invertible, then the adjoint is also invertible, and the inverse of the adjoint is equal to the adjoint of the inverse. Proof. Well, for A to be invertible, there must exist a matrix A inverse such that A inverse times A is equal to the identity operator. However, if those two operators are equal, their adjoints must also be equal. However, previously we saw that the adjoint of the identity operator is equal to itself, and the adjoint of a composition is equal to the composition of the adjoints in the reverse order. Thus, we have found that if we multiply the adjoint of A by the adjoint of A inverse, that equals the identity map. Consequently, that means that the inverse of A adjoint must be the adjoint of A inverse. Notice that all of these properties that we have derived thus far come simply from the definition of the adjoint. We know that all linear maps on finite dimensional vector spaces must be representable by an M by N matrix. Consequently, the adjoint of an M by N matrix must be an N by M matrix, but we don't even know what that is yet. However, nevertheless, we can already see that the adjoint is very similar in its properties to that of the complex conjugate. For example, the conjugate of a complex number is itself. The adjoint of a linear map is itself. The conjugate of a sum of two complex numbers is the sum of the conjugates. If A1 and A2 are linear maps mapping U onto V, then the adjoint of the sum is the sum of the adjoints. Similarly, the conjugate of a difference is the difference of the conjugates, and the adjoint of the difference of the linear maps is the difference of the adjoints of those linear maps. Now, the similarities don't always hold. After all, for complex numbers, complex number multiplication is commutative. Therefore, the conjugate of a product is the product of the conjugates. However, matrix or linear operator composition is not commutative. So therefore, we cannot say that the adjoint of a composition is the composition of the adjoints. Instead, we saw that the adjoint of the composition of B and A is the adjoint of A composed with the adjoint of B. Also, for linear operators, recall that if Z is a non-zero complex number, then the conjugate of the reciprocal is equal to the reciprocal of the conjugate. The same holds for linear operators that are invertible. The adjoint of the inverse of a linear operator is equal to the inverse of the adjoint of that linear operator. Also recall that the conjugate of z raised to the power n is equal to the conjugate raised to the power n. Similarly, if we are to compose a linear operator A with itself n times, then the adjoint of that, you should be able to deduce at this point, is equal to the adjoint of A composed with itself n times. All right, thus we see that the properties of the adjoint very closely follow, but not always, the properties of the complex conjugate. Following this topic, you now understand a number of properties of the adjoint, but not only that, you are aware of the parallels in the properties between the properties of the adjoint and the properties of the complex conjugate, including, for example, the conjugate of 1 is 1. The adjoint of the identity operator is itself. The complex conjugate of 0 is itself. The adjoint of the 0 map is the other 0 map mapping in the opposite direction. Similarly, we saw lots of all other properties are the same, with the one exception that because complex multiplication is commutative, the conjugate of a product is the product of the conjugates. However, for linear maps, the adjoint of a composition of B times A is equal to the composition of the adjoint of A and the adjoint of B. Here are the references, acknowledgements, the colophon, and a disclaimer. Cheers!